Hi all. In this video, we're going to take a look at an example solution to a problem that appeared in the University of Waterloo's 2024 Junior Canadian Computing Competition. We'll first go through the problem description together. We'll then outline an algorithm we can use to solve the problem. The contest provides 2 example input files. We'll walk through how the algorithm solves these cases step by step. We'll then take a look at a couple of possible solutions, one in Python and another in C. So let's get started. Here is the problem statement taken verbatim from the contest. There is a wildly popular new harvest simulation game called Harvest Waterloo. The game is played on a rectangular pumpkin patch which contains bales of hay and pumpkins of different sizes. To begin the game, a farmer is placed at the location of a pumpkin. The farmer harvests all pumpkins they can reach by moving left, right, up and down through the patch. The farmer cannot move diagonally. The farmer can also not move through a bale of hay, nor move outside the patch. Your job is to determine the total value of all pumpkins harvested by the farmer. A small pumpkin is worth $1, a medium pumpkin is worth $5, and a large pumpkin is worth $10. Here is the input specification, also taken verbatim from the contest, along with one of the example data files. Let's go through the specification now. The first line of input is an integer r is greater than 0, which is the number of rows within the patch. The second line of input is an integer c greater than 0, which is the number of columns within the patch. The next r lines describe the patch. Each line will contain C characters, and each character will either represent a pumpkin size or a bale of hay. S for a small pumpkin, M for a medium pumpkin, L for a large pumpkin, or an asterisk for a bale of hay. The next line of input is an integer A, where A is at least 0 and less than R. And the last line of input is an integer B, where B is at least 0 and less than C. Row A and column B is the starting location of the farmer, and the top left corner of the patch is row 0 and column 0. If you haven't tried the problem yet, why not pause the video and try it now? When you're ready to go on, hit play again. So here is the algorithm we're going to use in this video. It's a basic depth-first traversal algorithm in which we're treating each cell in the patch as a node in a graph with edges leading to its neighbors to the right, top, left, and bottom. We start off by pushing the pumpkin where the farmer is, along with its position, to a stack. And then we start the main part of the algorithm. This is to pop a pumpkin from the stack, take the associated value of the pumpkin, and then add the neighbors of the cell the pumpkin was taken from, if any, to the stack. We then continue doing this, popping the stack and pushing the neighbors until the stack is empty. So let's see how this algorithm works, step by step, on the first example file provided in the contest. Here we can see the provided data file on the right, along with an illustration of the pumpkin patch described. The first step is to push the pumpkin where the farmer is, highlighted in yellow here, to the stack. We then pop the stack and take the value of the popped pumpkin. It was a small pumpkin, so we only have $1 so far. The next step is to consider where the popped pumpkin came from, shown as a square here, and then push all the neighboring pumpkins to the stack. Once we have pushed all the neighbors, we're ready to pop the stack again. The popped pumpkin was once again small and only worth $1. So far, we have thus collected $2. Again, the next step is to consider where the popped pumpkin came from and push the neighbors to the stack. In this case, there was only one neighbor. Now it's time to pop the stack again. This time we got a large pumpkin worth $10, so our total score is $12 so far. When we look at where the pumpkin came from, we see that there are no neighbors to push to the stack, so we're ready to pop the stack again. We got another large pumpkin, so our score has increased by $10 to $22. The pumpkin we just popped has a single neighbor, so let's push that neighbor to the stack. And we're ready to pop the stack again. This time we got a medium pumpkin worth $5, so our total score has increased to $27 so far. The popped pumpkin's position does not have any neighbors, so we can pop the stack again. That was the last pumpkin in the region. Since it was a large pumpkin, our score jumps by $10 to $37, and we're done. Now let's take a look at how the algorithm works on the second example data file in the contest. This is pretty much the same pumpkin patch as before. However, 3 of the bales of hay have been turned into pumpkins, and the farmer is at a different starting position. This time the region the farmer is able to access has a more interesting shape. So let's start the algorithm. The first step is to push the pumpkin where the farmer is to the stack. We then pop the stack and take the money. Next, we push the neighbors to the stack. Pop the stack and take the money. Push the neighbors to the stack. Pop the stack and take the money. Push the neighbors. Pop the stack and take the money. Push the neighbor. Pop the stack and take the money. No neighbors. Pop the stack and take the money. No neighbors. Pop. No neighbors. Pop. You get the idea. Let's just watch the rest of the algorithm play out. And the stack is empty. We're done with $88. Okay, so now let's start thinking about how we might actually represent this data on the computer. A natural idea is to use a 2D array. That way we could use the array indices to represent the pumpkin's positions and the values stored in the array to represent the pumpkin's values. So here's the same pumpkin patch as in the previous example, but this time with the pumpkin values in a 2D array. We'll use 0 values to represent the bales of hay. As before, we start by pushing the value and the position of the pumpkin where the farmer is to the stack. After we push a pumpkin to the stack, we remove the pumpkin from the patch by writing in a 0 value to the cell we took the pumpkin from. This is equivalent to replacing the pumpkin with a bale of hay, which effectively marks the node as visited and ensures that the pumpkin cannot be added to the stack again later. We're now ready to pop. Push the neighbors. Pop, and so on. Let's just watch the algorithm play out from here. And finally, the stack is empty. We're done with a score of $88. Great. Now let's look at an example Python implementation. The first thing we need to do is read the number of rows and columns from the first and second line of the input file. We're now ready to start reading the actual pumpkin patch data. Here, we just have a dictionary that maps the pumpkin characters used in the input file to respective scores. We can then create a 2D array using an embedded list comprehension. We map each character in a line to the respective score to create a row of integers in the 2D array, and then repeat for each row. We then read in the row and column of the farmer's position from the last two lines of the data file. Here, we've created a stack as a simple list of tuples. The tuple represents the row, column, and value of a pumpkin pushed to the stack. Note that, at the time of making this video, the Canadian computing competition uses a really old version of Python 3 on its servers, so type annotations like this will not be accepted. If you want to submit your code to the contest grader, you can just replace this with an empty list. We then start off by pushing the row, column, and pumpkin value where the farmer is to the stack. Since we're using a list for the stack, this can be done with the append method. And then we remove the pumpkin from the patch by writing in a 0 value. Let's keep track of the money we collect. And we're ready to start. In Python, a list is a so-called truthy object. If we use a list as a Boolean expression as we do here, it is equivalent to false if it is empty and true if it contains any elements. So here we're effectively starting a loop that will continue as long as there are any elements on the stack. Inside the loop, we can pop the row, column, and reward associated with whichever pumpkin is at the top of the stack. Collect the reward, of course. And then consider the neighbors of the cell the pumpkin came from. To get the right neighbor, we look at the cell in the same row but one more than the current column. Then the top neighbor, in other words the cell in the same column but one less than the current row. Then the left neighbor. And finally the bottom neighbor. We want to make sure we don't go out of bounds and that there is actually a pumpkin in the neighboring cell. In Python, an integer is also a truthy object. If an integer is used as a Boolean expression, it is equivalent to false if its value is 0 and true otherwise. So this condition prevents us from adding any bales of hay to the stack or pumpkins that have already been harvested. If all the conditions are met, we can go ahead and push the tuple with the neighbor's row, column, and value to the stack. And of course, we mustn't forget to set the value in the neighbor's patch to 0 so that the pumpkin won't be added to the stack again at a later point. And that's pretty much it. When the stack is empty, we simply output the value of the money we have collected. Now let's take a look at a C implementation. In this example, we're actually going to implement the stack ourselves using a dynamic linked list. Let's include standard I/O for input and output and standard lib since we're going to be allocating and freeing memory both for the stack and the array of pumpkin values. Here we define a structure for the stack elements that play the role of the tuples we used in the previous Python solution. In other words, that store the row, column, and reward we get from pumpkins in the stack. It also contains a pointer to the next element in the stack so that we can link elements. Next, we create a pointer that always points to the top of the stack and set it to null for now, which we can interpret as meaning there are no elements in the stack. Then we can push elements to the stack like this. First, we create a temporary pointer to point to the element at the top of the stack or null if there are no elements. Then we allocate memory for the element being pushed to the stack and populate its row, column, and reward properties. And then finally we connect the new element to the previous top of the stack. We can then pop the stack like this. First, we indirectly assign values to the variables passed by address. We then create a temporary pointer that points to the second element in the stack if it exists, otherwise null. We then free the memory used for the element at the top of the stack. And then finally reconnect the head to the stack. To check whether the stack is empty is then straightforward. We simply check whether the head's pointer is null. Here we have just set up a few preprocessor definitions to make some of the code that comes later a bit cleaner. Pop will send the addresses of variables r, c, and reward, which will exist in a later context, to the pop function we created earlier. These variables will represent the row, column, and reward of a popped pumpkin respectively, and we might as well add the reward to a variable total that will exist in a later context here too. OK to push neighbor will check whether a neighboring cell is within bounds and whether it contains a pumpkin, again using variables that will exist in a later context. And push neighbor will push a pumpkin and its position to the stack if appropriate and remove the pumpkin from the patch. And finally, we're ready to begin. Here are variables to store the number of rows and columns in the pumpkin patch, the position of the farmer, and the total reward collected. We also create a dummy character to use while reading the pumpkin patch data. We can then read the number of rows and columns from the first two lines in the data file. Here, we're allocating memory needed for the pumpkin values. Patch is a pointer to a sequence of integer pointers, which is why we have the two asterisks. And we need enough space for as many integer pointers as there are rows. For each row, we allocate enough memory to store as many integers as there are columns. After we previously read the number of columns, we're actually sitting on an end-of-line character, so we can flush it by reading in a single character. And then we're going to read the characters of the pumpkin data in the data file one by one. Which character we read determines the pumpkin value at the respective cell, and the assumption we will encounter one of these characters is okay for this problem. Now that we have read in the pumpkin data, we can just read in the position of the farmer from the last two lines of the input file. So here's the first step. We push the farmer's position and the pumpkin value where he is to the stack, and then remove the pumpkin from the patch or replace it with a bale of hay if we want to interpret it in that way. Then we're ready to start the main part of the algorithm. While the stack is not empty, we're going to alternate between popping the stack and pushing the neighbors of the popped pumpkin to the stack. If you recall, the pop preprocessor definition reads values into the r, c, and reward variables and adds the reward to the total. And then we look at the neighboring cells of the popped pumpkin. Here we're looking at the cell to the right, in other words, the cell with the same row, but whose column is one more than the current column. We now have the row and column of the potential neighbor stored in nr and nc respectively. If you remember, the OK to push neighbor preprocessor definition uses the values of nr and nc to check whether there is a neighboring pumpkin at that position, and the push neighbor definition pushes the pumpkin position and value to the stack and removes the pumpkin from the patch. We then repeat for the cells above, to the left, and below the popped pumpkin's position. And when the stack is empty, we simply output the total. Just as a good habit, we should of course free the memory we allocated for the pumpkin patch. And we're done. So there we have it. Thanks for your time. I hope you enjoyed the video. If you solved this problem using a completely different strategy, be sure to share in the comments below.